Let's get on to our next talk. And the next talk is going to be by Professor Paul Thibado. Paul is a professor at the University of Arkansas. He got his bachelor's in science, in physics and mathematics at San Diego State, and his Ph.D. at the University of Pennsylvania. He works on surface physics and using scanning tunneling microscopy. And in particular, for the last 10 years or so, he's been looking at freestanding graphene films. If you are like me, you've been aware of Paul's recent work for the last few years and have really been scratching your head about it, because he has some intriguing and fascinating results in terms of harvesting essentially Brownian type motion in graphene. And it's very interesting and may really require some basic rethinks of a lot of the thermal vibration concepts that we've had. So Paul, please, the talk title is Charging Capacitors Using Graphene Fluctuations. Paul.
Great, yeah, thank you for that. You know, I guess my video has been stopped by somebody, so you can't really see me, but let me see if I can share my screen.
Paul, you can just start your video yourself.
You know, it won't let me.
It won't let you, huh?
It says you cannot start your video because the host has stopped it, but that's okay. Can you see my screen?
Yes.
Okay, so my video is off, but it's not my doing here, sorry. All right, oh, great. The host has asked me, so let's start it. Yay! All right, great. Thank you. Okay, well, thank you for that introduction, Garrett. Also, yeah, well, I'm Paul Thibado of the University of Arkansas. Let me just get that out of the way. And I also want to thank Daniel, and Garrett, and Charles for talking to me and being interested in my research. I've had great conversations with them. I'd also like to say that the talk that Daniel gave was excellent. That's the first I've heard his talks. It was really well done. I do want to clarify a little bit that my research is not about searching for violations to the second law. My research is about harvesting energy from the environment. So I'm just going to kind of focus on that part of it. But I do talk about the laws of physics, of course. And so let me just get started with that. Start a little timer here. My talk will probably only take 35 minutes, so there'll be plenty of time for questions if there are any. I'm going to talk about charging capacitors using graphene fluctuations. This is the circuit that I'm going to use. We've actually been studying this circuit for about 5 years now. I'm going to show you that this circuit can steal energy from the thermal surroundings. These results actually were really just discovered and presented here first. It was kind of good timing that I got contacted by Daniel and Charles and Garrett. In the first part, I'm going to talk about the deterministic properties or solutions, if you like, of this circuit. And then the second part, I'll talk about the stochastic part. Let's see if this is all right, good. Okay. So in the deterministic part, it's this thing up here. Maybe I can get that out of the way, okay. So in the deterministic part, all right, graphene, it's only one atom thick. Therefore, it's extremely flexible. A measure of that flexibility is called the flexural rigidity. It's given by D. Here's the formula for it. The important part is it has this parameter h to the third power, where h is the thickness of the plate. So graphene membrane is only about 1 nanometer thick, whereas you could probably make a silicon nitride cantilever at best 10 nanometers thick. That'd be the thinnest. So right here, that would tell you that the graphene is going to be 1,000 times more flexible than this cantilever. What that translates into, if you think of kind of like Hooke's law or whatever, if a 1 nanonewton force moves the silicon nitride cantilever a certain distance, then a piconewton force 1,000 times smaller could move the graphene the same distance. So it's very flexible and it's easy to move. When graphene moves, how does that result in energy harvesting? I like to turn people to this paper. It's out of the physics teacher. It basically talks about variable capacitors. If you look at the definition of the capacitance, it's how much charge it can store divided by the voltage you've applied to it. If we look at the change in capacitance at a fixed voltage, it'll result in a change in charge. Here's a nice illustration of a parallel plate capacitor connected to a battery, and it has 4 units of charge on it. If we applied a force to this plate and pulled it to the right, the capacitance would go down, so the charge has to go down. So what'll happen is, let's say these 2 charges will flow counterclockwise. They'll go backwards through the battery and recharge it if it's a rechargeable battery, and then come around here to cancel these charges. And the force that pulled that plate apart, that's what's doing the work here. So that's basically the fundamental operation of our circuit as well. So as the distance between the graphene and the electrode changes, because the graphene's so flexible, it's moving all the time under the slightest influence, the capacitance will increase and decrease, and then the charge on the graphene will also increase and decrease. When current flows in this circuit clockwise, it'll go through diode 1 and charge capacitor C1 to complete the circuit. When it flows counterclockwise, it'll charge C2 going through D2 and go back to complete the circuit. So that's basically how the energy harvesting will work. Take an AC signal and charge these 2. We had an illustration we made of this a while back. See if I can get it to go. Here we go. So this is the idea. So basically there's the graphene fluctuating, nice slow motion. As the capacitance increases, the charge increased there, and it took power from the battery. But now the battery got recharged, and we also made it go through that storage capacitor. This is like that C2 over here. And as the graphene keeps moving, it'll keep forcing charge onto the capacitor and off the capacitor. And we use these diodes to redirect the current so it can charge up the storage capacitor, and then we can use that later to do something useful. All right, what about the efficiency? So we actually built this circuit. Here's a variable, on a macroscopic scale. So here is a variable capacitor. You can vary the capacitance by turning this rod here. Here, all these plates are overlapping one another to give the maximum capacitance. In this picture, they're not overlapping at all, and it gives you the minimum capacitance. This plot here shows the capacitance as a function of rotation. It starts off at about 1 nanofarad, drops to 0.1, moves in a nice linear line actually, and goes back to 1 again as you continue to rotate it through a full rotation. This is a really high-grade military variable capacitor that we did with this experiment, so it has this nice precise capability. We hooked it up to this circuit. That's the same circuit. We used transistors wired as diodes here. They were a little bit better for this application. And so what happens is that when the current goes clockwise, it'll charge capacitor 1. And when the current goes counterclockwise, it goes backwards through the battery and charges capacitor 2. Here we're showing the voltage on capacitor 2 as a function of the number of rotations, so you can see that it's charging it up. We can also measure the current flowing into capacitor 2 in time. It has a kind of a spiky nature. It's pretty small, it's only 10 nanoamps, but it's wider here as the time goes on or the rotations go on, it gets narrower, so the current's dropping as the capacitor is charging up. The interesting thing that we found was the circuit has 50% efficiency when operated at the maximum power point. So even though the current was small here, and people thought, okay, well, it'll work, but the efficiency will be terrible. Turns out actually the efficiency is excellent. 50% efficiency is very good. Here's a little video of it running. So here's the variable capacitor being turned by a motor, so it's nice and smooth and continuous. This voltmeter back here is measuring the voltage on capacitor 2. You can see it's increasing in the negative direction. And here's a little breadboard with the circuit on it. And in fact, we've been pushing this forward as hard as we can, and we've actually made a first integrated circuit or a chip in 2021. This is a 5mm by 5mm chip. We had it made at Taiwan Semiconductor. Inside the chip is the diode circuitry, and it connects to these bonding pads around the outside. So there's a bunch of bonding pads here. There's a big section here in the middle, which is basically we left blank. And when the chips came back, we did post-processing. We built an array of these graphene electrode systems on this chip, and then connected those things to the bonding pads or the circuitry below. You can see the graphene here. Graphene's covering the whole upper half of the chip, touching the bonding pads naturally there. The lower edge of the graphene can see right here. So we're pushing this forward as hard as we can. All right, so that's what I'm going to call the deterministic part. Let me ask this question. So when the graphene shakes, it's not really a question, but let me point out something. I'll get to the question below. So when graphene shakes, current flows and the diodes charge C1, C2. So hopefully I convinced you of that. But here's the question. Will C1 and C2, will the capacitors charge if the only force acting is the thermal force? And if everything's at the same temperature? Well, what's motivating this? We had some early success. We were able to show that the Brownian motion, that's that thermal motion of graphene, could power a circuit. We did this using our scanning tunneling microscope chamber. This is a TEM grid with graphene overlay. You can see the graphene film here. This is pretty much the same circuit, except we have ammeters here measuring the current in these two channels. And so we could do that. We did power a circuit. And we determined that the power density was 1 picowatt per micron squared. If you convert the units on that, that's 1 watt per meter squared. There was a really nice study done in 2018 I want to draw your attention to that studied wind farms all around the world. There's thousands of them. And they found out that wind farms produce 0.5 watts per meter squared. So actually we're on the par with wind power here. Solar farms all over the world were also studied. They only produce about 5 watts per meter squared. So it's a viable, it's worth pursuing, I guess is what we would say. This paper obtained a lot of attention. One way you can measure that is through this altmetric score. If it got a 286, well, it's up to 286. Most of my papers get a 0 or a 1 in this altmetric score. Honestly, to get a higher altmetric score, there were other papers in that year. If you found a vaccine for COVID and published that, you got a higher altmetric score, or if you found water on the moon. So this is a big score. And actually, I got close to 1,000 emails. I'd say most were fan mail, but there's a few haters out there. Usually the questions were about the second law, so I think that's partly why I'm here. All right. So let's move to part 2, the stochastic part. So to do that, we're going to talk about Brownian motion and the Ito-Langevin equation. This is basically Newton's second law, but with a stochastic driving force. So I've written that here. This is MA. The forces that are acting, there's a drag force that's involved in Brownian motion that basically is trying to bring the Brownian particle to a dead stop, and it will bring it to a dead stop. But then there's a thermal force that is also present, and this thing transfers energy from the thermal environment to the Brownian particle, gives its energy to the particle and gets moving again. Let me show this little video. So this is like our Brownian particle. This is in 3D, but our solutions will be in 1 dimension. The drag force is taking the kinetic energy of the particle and giving it to the environment. And this force over here is taking the energy from the environment and giving it back to the particle. This thermal force looks a lot like this. It's basically kind of a noisy stochastic signal. What we want to do is steal energy from this force. Notice the thermal force is 0 if T equals 0, the temperature is 0. That's how we know it's the thermal force. Also notice that eta, this parameter, is in both places. It's both here in the thermal force and in the drag force. This ensures that we reach thermodynamic equilibrium. This was a big breakthrough in the fluctuation dissipation theorem. Basically, what it says is if the particle is giving energy to the environment, and the energy is giving, and the environment is giving energy to the particle, if those two processes are equal to each other, then we'll reach thermodynamic equilibrium. And that's basically saying that the kinetic energy, 1/2 mv squared, is equal to the thermal energy, 1/2 kBt. So by doing this, we ensure that. Graphene has a Ripley structure. This is an important property. We think of graphene, the surface of graphene, like this, except dynamic, more like the surface of the ocean. It has waves on it and it has curvature. We call these ripples. The ripples can have a convex curvature or a concave curvature, and they can invert their curvature as well. So here's kind of an illustration of a ripple that is convex, and it could flip over and become concave. We've done molecular dynamic simulations of graphene ripples, and sure enough, they do that. So here's a ripple having this random motion, but at a positive value here. And then at this point in time, it flips its curvature from convex to concave and goes on a long excursion, and now sits down here for a while and goes back again. So that means it lives in what we call a double well potential. It can either be at this 0.5 or minus 0.5 instead of 0. So the force from the ripple double well potential, that needs to be added in, so we add that in. What we found it does is it lowers the frequency of the energy, which is helpful for energy harvesting. We still have this, there's still thermodynamic equilibrium. All right, we're gonna hook it up to a circuit. It turns out electrons in a circuit also basically have Brownian motion. So there's an Ito-Langevin equation for this as well. Let's start over here. Here's a circuit with a capacitor and a resistor. I'll tell you this can't harvest energy. I'll show that it can't. What we start off with is Kirchhoff's loop law. It says that the voltage on this capacitor is Q over C, but it's also I times R. Instead of using the resistance, we're going to use the conductance. It's just 1 over the resistance. So I equals the conductance times the voltage. We put that here, so I is dq dt. It's the conductance times the voltage. And then we add the thermal current this time. So here the resistance is trying to bring the electron to a dead stop, and it will. But then the thermal current comes in, gives it a kick, and starts it moving again. The thermal current is 0 if the temperature is 0. Notice mu is in both places again. So this is going to ensure that we satisfy the fluctuation dissipation theorem and that we're in thermodynamic equilibrium. What that tells us here, though, is that the 1/2 kBt is equal to the energy stored on the capacitor, which is 1/2 C voltage squared, U squared. If we rearrange that, it says U squared, the variance of U, we say, is kBt divided by C. So notice the smaller C is, the larger the voltage becomes. So I plotted that here. So even though the mean voltage or the average voltage is 0, the fluctuations or the standard deviation of the voltage increases dramatically as C becomes smaller, and we're going to take advantage of this. All right, let's replace the resistor with a diode. That we can't do anything with the resistor, we need a diode. So here's a capacitor with a diode. I can tell you this circuit will not harvest energy either. I can prove that, I will. The diode is special in the sense it has a nonlinear conductance. So it has a mu prime. Basically, there's a rate of change in the diode conductance with voltage. That's an added effect. With a resistor, this would be equal to 0, but in a diode, it's not 0. Well, look what happens to the Ito-Langevin equation. We get this extra term stuck in here. This is called the thermal drift current. This drift current is 0 if t equals 0. See that? It's also 0 if mu prime goes to 0. So if this diode turns into a resistor, it's gone. But here's something. Okay, why is this term here? Okay, look over here. So mu is over here to maintain the fluctuation dissipation theorem. But now mu keeps changing in time. It's actually also a stochastic variable now. So this is very complicated. This took a long time to figure out. What's happening is we have a noisy term mu times that thermal force, which we know is noisy. That gives us multiplicative noise. That's extra noise, and it's complicated. Now, you have to correct for that to maintain the fluctuation dissipation theorem. It's a nonlinear effect, and that's what gives us this term. So this drift current is basically ensuring that there's no net current flowing at any temperature. Basically, we achieve detailed balance. It's because of this multiplicative noise, we've got to correct for this here. It's an exact correction. But here we find a hint that we might be successful at energy harvesting. So if we look at the steady state, that is if I goes to 0, if the current stops flowing, that's the steady state solution up here. This term, this voltage, can't be 0. It needs to equal this term. So we have a voltage that must be present in the diode at some temperature T. So that voltage is non-zero. That's giving us a hint that we're going to find something here special. All right, let me just chat about the diodes real quick. We do need diodes. They have to be real diodes. That means they have to be leaky diodes. For convenience, we parameterize the diodes with a sigmoid function, which is what this is. So this is the conductance. The only parameter here, which is convenient, is U0. If U0 is set equal to 0, it's called a perfect diode. It'll have no conductance in reverse bias, and it'll be have perfect unity conductance in forward bias. So it's controlling the leakiness. If we let U0 become really large, then the conductance flattens out. In fact, it turns into a resistor. Here's some IV characteristics. You can see that they're leaky, they're non-ideal. I mentioned that the rate of change in mu is important, so I'm just plotting that here. As U0 gets smaller, this derivative gets larger and larger at 0 volts, and it's symmetric. All right, so here's the full system. Sorry, I have a lot of math here. The Ito-Langevin equations with Kirchhoff's laws. So let's write down Kirchhoff's loop laws. I'll just point them out to you basically. There's 2 loops in this circuit. There's a diode 1, C1 to the capacitor. There's the there's the diode voltage right here. It's going to be this voltage plus this voltage. We're going to let V equal 0 from now on. And then the other loop is going through the second diode, the second capacitor, and then the graphene. Okay, so those are the 2 loops. We also have a Kirchhoff's junction law. So any current that's coming from the graphene hits this junction and gets split. So there's an I1 goes this way and I2 goes this way, and they have to add up to I. If we set all the initial charges on these 3 capacitors to 0, we can rewrite this junction law as just Q is Q1 plus Q2. What I want to point out here, just to give you a little foreshadowing. This is an algebraic constraint. It's just conservation laws imposed on our stochastic equations. These will have profound consequences, we'll see. So here's our 3 differential equations. This is the Brownian motion for the graphene. I added one more term since the graphene's near the electrode and it can have charge on it. There's a Coulomb interaction. This Q is stochastic and we square it. So there's more multiplicative noise here. It's very complicated. There's the 2 differential equations for the current. I is 1 and 2 here. Those are the same as I wrote down before. So in the end, we have 3 coupled, stochastic, nonlinear, stiff, differential equations. They have to be solved numerically. Give a little shout out to Mathematica here for the earlier talk this week. I recommend using Mathematica to solve these. Look, we're going to look for solutions very far from equilibrium. You have to do it numerically. There's actually a very large parameter space here. It took us 1.5 years now to study this parameter space. We just wrapped this up. We've been using a supercomputer. We have 10 billion time steps for each simulation, and each one we do with 3,000 realizations and a huge parameter space on top of that. So here's our surprise discovery. Charge is added to capacitors 1 and capacitor 2, and energy is harvested. Here's a plot showing the charge on all 3 capacitors in time. Let's start with the blue one. The blue one is the graphene. The graphene doesn't build up any charge. Well, most of the voltage is set to 0. So that's going to keep the charge here at 0. And so it just fluctuates a little bit and stays zero the whole time. But look at this green one. The charge rises quite quickly and reaches a steady state close to 20. This is Q2, so this is the charge on C2. The red one is decreasing, building up a negative charge on it until it gets to about -20 and reaches a steady state. That's C1. Notice that Q1 and Q2 are strongly anti-correlated. Anywhere Q1 goes, Q2 has to do the opposite. There's a strong anti-correlation here. This is coming about because of Kirchhoff's laws. So how can this circuit harvest energy from the thermal environment? There's 3 ingredients we believe are needed. The graphene, which is the very C of X capacitor here, we need it to be much, much smaller than the storage capacitors. This boosts the voltage to really high levels for the diodes. The diodes generate multiplicative noise. I pointed that out to you. There's multiplicative noise in diodes that shifts the voltage, the diode voltage, away from zero, so we can have a persistent voltage. We also need this junction here. The junction, in fact, the junction has to be followed by diodes wired in opposition. We've run the simulations with the diodes oriented in the same direction. You can't harvest energy then. We've also cut off this loop. If you force Q2 to go to 0, then Q1 goes to 0. You need these 2 loops, you need the junction. You can kind of see that here. We have that Q is equal to Q1 plus Q2. If we look at the time averages or ensemble averages, we know Q is 0. So that says that Q1 is negative of Q2. If we square this thing, that's kind of talking about the energy. Q1 squared plus Q2 squared is going to be Q squared minus 2Q1. This is a correlation function here, really, between these stochastic variables. We can see Q1 squared. It's just -20 times -20. It's 400. Q2 squared is also 400. Q squared is 0. And then -2, this is Q1 times, it's 20 times -20. So the anti-correlation of Q1 and Q2 is driving the energy harvesting. It's responsible for it. You can see that here. Let's look at the ensemble averages. If you plot the, if you plot the capacitor charge as a function of capacitance, the storage capacitors capacitance, we find that you'll store more charge if you have a bigger capacitor. In fact, it's linear, precisely linear in that. What does that mean? It means they're all being charged to the same voltage. That's that diode voltage I pointed out. There's some persistent diode voltage, it's being held here. Now let's look at the diode parameter. Turns out you can maximize the charge stored on the capacitor if the diode parameter is about 0.15. And very interestingly, if the diode parameter gets smaller and smaller, we've followed this all the way to 0, it goes to 0. It's exactly 0. If you have a perfect diode, you can't harvest energy. On the flip side, if the diode parameter gets larger and larger, it also goes to 0. That's because it turns into a resistor. So you can't harvest energy with a resistor. If you look at the ensemble averages in the capacitor charge, that earlier one was 1 realization. So we do 3,000 realizations. You get these nice smooth capacitor charge versus time curves. In fact, they're exactly RC charging circuits. If you look at the time constant, tau, of the RC circuit, which is R times C, it's perfectly linear in capacitance. So it's exactly like the RC charging, which I showed you in the deterministic. So then we can look at the charge, the voltage, the current, and the power as a function of time. So here's the capacitor charging up. That allows us to determine the voltage on the capacitor. It's continuously rising. We can also get the current. So see, the current starts high and then decays exponentially in time. If you take the current times the voltage, you'll get the power. And look, there's a peak power. Remember, I mentioned the peak power. This circuit has 50% efficiency. There's the peak operating power right there. All right, can we really find the source of energy? We can, in fact, using what's called stochastic thermodynamics. So this is an emergent field of physics, honestly, with low-hanging fruit. You know, anything we look at, it's never been seen before. It's revealing a lot of nice things. So basically, it allows us to look intimately at all the sources of energy, heat, and work. So here's the graphene heat bath. We can track what it's doing. Here's the graphene drag, the resistance, basically, the losses. There's the resistor dissipated power, and there's the resistor's heat bath. So what we do is we write down the energy of the system. That's straightforward. We use the first law of thermodynamics, says the energy is the heat plus the work. And then we go ahead and we calculate the heat from the point of view of the graphene. You have to pick some point of view. The heat flux produced by friction is this formula. These are these two terms over here. Those, in fact, during the energy harvesting phase, we calculate those precisely. This is zero. There's no heat. There's no heat flux produced by graphene. Turns out the work, so this term here is zero. So all of the energy is coming from the work. Well, the work done on the graphene by the circuit, that's given by this, a little bit complicated, and you can't write it analytically, but it's close to this term, this KBT over RC. That's the power of the thermal bath being put into the diode, basically. And this is the dissipated power by the diode. Well, here's what happens. During the energy harvesting phase, while the capacitors are charging up, this term, the thermal power coming from the thermal bath, is slightly bigger than the dissipated power of the diodes. And that extra energy charges the capacitor. So that's the source of power. We can prove that. Here's a graph of that. So the red line here, these all start at zero, but the red line is the energy of the system. So this is the charging of the capacitors. Of course, they're storing energy, so their energy is changing in time. The green one is the work plus the heat, but we also separately check the heat. It's actually zero. So this is really just the work. If you subtract these two, they're basically always zero. This is actually, it's numerically challenging. There's some slight numerical drift here that's happening in time, which we work very hard to deal with. But notice how this hairiness goes away. This tells us the first law is rigorously obeyed at every time step. This is what this is telling us. So we are satisfying the first law of physics, which is here. So energy is increasing in time as the capacitors charge up, so H is growing. Graphene does not provide any energy, Q is zero. The power comes from the thermal bath of the diode, so the work done is what's giving us the energy. The graphene does provide the voltage, though, at these top rails. So this is a very interesting thing, why you need these two loops. So current actually flows between the diodes, basically forming a vortex here. The circulating current is here, charging one positive, the other negative. And all the power and the current is here, even though the voltage is set by this guy over here along these top rails. Again, V at zero here. Very interesting. All right, what about the entropy? The measure of disorder. We can track the entropy during charging using the Shannon entropy formula. It basically looks at the probability of having a certain charge in time. All right, so we have those 3,000 realizations, so everything's the same except the random numbers change. We always start with Q equals zero, and then we track Q1 and Q2 in time, just like the graph showed before. And then we find the probability of having a specific set of charges, Q1 and Q2 at a specific time. All right, so here's the graph of the entropy. It starts off at zero, I'll explain that in a second, but then jumps fairly quickly to around 4. There's a slight decay in the entropy here. We should chat about that. Maybe Daniel might chat about that. But anyhow, there's an overall positive production in entropy from 0 to 4. Entropy is produced here. At T equals 0, let's see what's going on there. So the initial conditions are that there's everything set to 0. So for every simulation, they all have the same initial conditions, whatever, that doesn't matter. So there's 100% probability of having the same initial condition, and the log here, which comes in here, the log of 1 is 0. So the entropy starts off at 0 and it's positive. We have a positive production of entropy, so we're happy with that. All right, let me just throw out some, I got a lot of email, get lots of questions. Let me just guess some questions and throw out some answers here. Does our energy harvesting system violate the first law of thermodynamics? No. The energy is equal to the heat plus the work. That's the first law. Actually, we found the heat is 0, so all the work is done to create the energy. Where does the stored capacitor energy come from? Well, it comes from the thermal surroundings. It's coming from this kBT over RC. So it's the environment, the thermal environment, stealing energy from that massive thermal environment that Daniel talked about. Is work done at thermodynamic equilibrium? No, our system's not in thermodynamic. The charges are always moving. They're always adding and removing from the system. It's actually very far from equilibrium. Is useful work done at a single temperature? Yes, everything's at the same temperature. We ensured that through those terms that I showed to you. Does our system violate the second law of thermodynamics? No, our system starts from far from equilibrium, and is driven to a steady state by unbalanced forces. I'll give a good example of this in a second. Those unbalanced forces, this is the diode voltage, it turns out, that extra term is driving it. Is entropy produced? Yes, the capacitor entropy increases from 0 to 4. Are there any pedagogical examples of thermal work being done at a single temperature? Yes. As a framework, consider the ideal gas, which Daniel talked about, so it's very helpful for this talk. So here, consider work and entropy during an isothermal expansion. So imagine two masses sitting on this balloon. We're going to remove the first mass. And as the mass gets removed, the balloon can kind of expand because the weight's been removed. And we're going to analyze the work done on this second mass as it is raised up a height h. We're going to have a heater here. We'll see we need to have that. So this is to keep the temperature fixed. We have before and after pictures here. Let's apply the first law to the second mass here, this one. Here's the first law. The heat, there's no heat change in this mass. The energy changed because it was raised, mgh, and the work was done. The normal force of the balloon pushed it for a distance h. So work was done on the mass, and the energy increased from that. This is exactly what I was saying in our situation. So work was done by the thermal environment on the capacitors, or on the circuit, if you like, and it raised its energy. And the heat was, there was no heat change. This is the same as ours. Now let's analyze the gas. This is the thermal gas. So here we know for an ideal gas that the work done in an isothermal process is given by this formula. Now here the work is done by the gas, so the work's negative. Let's apply the first law to the gas. Here is the first law. There's no internal energy to this gas, so it's ideal. So we're going to let H be 0. So that means that delta Q is equal to minus delta W, or positive. So that means heat flows to the gas. That's why we need the heater. So the heater heats the gas to keep the temperature constant. That heat is positive because it's flowing into the gas. That means entropy is produced and it's positive. These are all these are basically equal, in some ideal circumstances. So yeah, so that's for us, this is the thermal environment around the resistor. The heater, well, that's the sun. All right, so let me summarize. Stochastic thermodynamics is yielding quantitative insights far from equilibrium. Graphene, this capacitor C of X, I mentioned, shifts the power to low frequencies due to this double well. This has some technological value. The average capacitance of graphene determines the voltage. That's kind of like the gain or the bandwidth. You can think of, if you think of the, the impedance of a circuit, the imaginary part is the capacitance. So it can do something like change the gain or the bandwidth. But the current circulates between the diodes. That's the resistance. That's the real part. And it's doing the work here. Energy harvested increases in time and then stops. It reaches a steady state. It's not like some perpetual motion machine. It just it's trying to reach steady state. The capacitors would, normally in the room right now, a capacitor's charge would be 0, and that's its steady state. When you hook it to the circuit, it wants to be something else. That's its steady state. The energy source is the diode's thermal bath, because remember the heat was 0. Entropy was produced. It went from 0 to 4. Estimates of our power density, I mentioned there before, it's worth kind of pursuing these things. And then let me just acknowledge Pradeep and Saran. Been chatting with them for years about this. It's been extremely helpful. Also John New at UC Berkeley and Louis Vanilla at Carlos 3. These guys are world experts in stochastic thermodynamics. We couldn't move forward without them. We are summarizing this paper. Hope to get it on the archive before we submit it for publication here in a few weeks. And also let me thank funding sources here. With that, I'm done. Thank you very much.
Thank you. What a fantastic presentation. Your work is so careful and so fascinating. I'm sure there are going to be a lot of questions. I'll start off with a very quick one, and that is that you have described your system as being far from equilibrium and therefore not violating the second law. If you take your system of the graphene and you just start it in thermal equilibrium, what nudges it to be far from equilibrium if it isn't the system itself?
Let me escape out of this. Okay, so so for example, here, once the charges reach this steady state value, so that is the steady state solution to this set of this system. And that's not in thermodynamic equilibrium, but it is in a steady state. And if you start the system in the steady state, it stays in that steady state. If you start with the capacitors with more charge, let's say you started with 100 units of charge on the capacitor, it will lose charge until it gets down to 20. It's trying to get to here at this 20 level. And if you start it with 0, which is what we like to do, then it will rise to 20. So does that answer the question? That's basically what will happen.
Yes, so if you start from 0, from equilibrium, it goes into this far from equilibrium state spontaneously. And if you bleed the charge off, say into a motor or a resistor or something like that, will that happen continuously?
Yeah, so you could, it's ideal to run this type of circuit at the peak power. I think I have that here. So here's where you'd want to, that'd be the operating point for the circuit, basically, because then you're drawing the most amount of power from the thermal environment.
Right.
And so what you would do is try to hold it at that point by removing current at the rate that the current is coming in at. So it's stuck there basically, and you get the most efficient machine at that point.
Okay, we will have to talk about the implications. I think Schaefer is the next person. Schaffer has the next question.
Schaefer, yeah, Aiden Schaefer. Just real simple question on that. The chipset, the larger chip that you built, was that an even or odd number of capacitor diode pairs?
Well, we've done a whole bunch of things. We've made a bunch of chips. It's expensive to make these chips.
Okay.
We run lots of experiments on each chip, it turns out, as well. So you'll find pretty much anything and everything. You can, we were only able to prove that if you have one loop here, if you just do like a half wave rectifier, it won't work. If you want to harvest thermal energy, it won't work. It'll work in the deterministic case. I mean, if something's shaking the graphene, it'll work. But if you want to harvest thermal energy, well, then you need a full wave rectifier. Shockingly, it's a big discovery we just made.
In audiophile land, there's a capacitor diode ladder filter, and it only functions. All of the diodes are in one direction, but its job is to center a waveform that's going through it. So this is just reminiscent of that, but you have the diodes in opposite pairs for energy generation or opposing pairs.
Right, there's a lot of circuit topologies out there.
Okay.
And we've played with a whole bunch of them, and some are like a Cockcroft-Walton generator, a multiplier.
Right.
So there's a lot of really interesting. I kind of mentioned the low-hanging fruit here. I mean, each topology requires that you go through what we did in great detail, because it's hard to map from one to the next.
Right.
So really,
Math is-
I think that's why double E is its own field, because every topology you got to sit and take a look at it and see what it's going to do.
Okay, thank you.
I think there's a lot of opportunity here, though. Yeah.
Thank you. Daniel, you had a question.
Paul, thank you for just a marvelous talk, really nicely explained and very careful. I'm still at a loss. I mean, I think I understand what you're saying. Your system comes to a steady state, and as it's posed, as far as you've gone, I would agree that the second law is not violated. I agree with you on that. However, I don't feel you've really addressed the question. If you can constantly siphon off energy from each of these capacitors to do external work, then thermodynamics is pretty clear that if you are turning thermal energy into the capacitive energy, which you're claiming, and then you're using that energy to carry out external work, and if your capacitor continues to recharge, in my book, that's a second law violation. So I realize that you've circumscribed your system carefully, but could you expand it, please, to a situation where you're doing external work, let's say on something like what Garrett said, a motor or TV or whatever it happens to be. If it's doing external work, does it still not violate the second law?
Okay, well, this one took 1.5 years, and I always hate to speculate on like maybe the next circuit we should study or the next situation. But let me just say something kind of related, and I think it'll support my point and give some clarity to your question. We like to talk about Feynman's Brownian ratchet. He says if you stick a windmill in your room and the air is not flowing at all, then it's not going to sit and turn the windmill. Basically. So that's kind of a thermodynamic equilibrium position that you're sitting in. But I bet you don't disagree with this. If I take this mass off, this balloon will expand and raise it. So what we're really doing is we're creating a system that has an unbalanced set of forces that drives the system in one direction to balance out the forces, just maybe like water going off a waterfall. So there's unbalanced forces in the system, and they drive the system in one direction. Nothing wrong with the laws of physics or thermodynamics there. And that's exactly where this work comes from, is from those forces doing work. And entropy, and I kind of went through this nice little argument here. You can connect all the dots together in an ideal picture. I honestly thought, well, yeah, I should let you answer, but I kind of thought you might be interested. The entropy does decay. It's a well-controlled thing here. It does decrease in time as the capacitors charge. There's some organization that's happening as the capacitors charge. It's a very interesting thing, but anyhow, just thought I'd throw that out there. Yeah, so I kind of would point you to this. It's a non-equilibrium. There's unbalanced forces. There's no problem here with this thing doing work.
The difference here is that with the gas, there's internal energy that's then being converted into work, right? And if you add the mass back and you kind of revert to your initial position, there'll be no energy gain because all that energy goes back into the potential of the gas. Versus in your system, it sounds like you're able to complete a cycle and have this energy extracted. So I just not sure if the analogy.
Okay. Yeah. No. Thanks, Paul. So okay. So let's. It's a little different than I think you said there. If I take this mass too, and
You muted yourself. I think you're muted.
Paul, we can't hear you.
Oh, okay. Sorry. I'm back now. Somehow it muted me. Sorry about that. So okay. So let's go back to this picture here. So if I take the second mass, which I slid off, let's say, and I have to raise it to H and set it back down on here, and then it will compress this back down. So I have to do some work on the mass and then it'll compress the gas back. And I can now do work on the environment, put energy back into the environment from myself. So how do I do that with mine? Well, I take the capacitors away from the circuit. I hook them up to resistors. They discharge through the resistor, dissipating energy back to the environment.
Right.
It's the same thing, but I will give you something. There's something amazing going on here. I can put my finger on it. I can take that empty capacitor, hook it back up to the circuit. It will recharge itself. It's like I'm getting it for free. Here, I had to raise the mass to get it back to the initial condition.
Right. Yeah.
So there's some element of freeness here that's happening, but it's really because the diodes have this voltage in them, and they're trying to, their equilibrium is different than the Earth's equilibrium.
Sure.
Anyhow, it's a very interesting system, and I hope other people will look at it too.
Thank you.
There's so many questions. I just to push into what Paul was just saying. So both Daniel and I are talking about bleeding the energy off continuously as opposed to switching back and forth. Can you comment on that situation, please?
Yes. So so you're basically saying if I somehow hook up a circuit here with a resistor right here, so it draws current off this thing, but the rate of current is basically such that it doesn't just pull it all off, you know, it kind of does it at some certain rate. So basically that's going to be taking the energy of the capacitor, again, putting it back into the thermal environment that originally came from. You know, to some extent, you know, people I don't think really got this, but I like to think, honestly, this paper was almost more significant. Here we're powering the circuit directly from the thermal environment. And it's doing work, it can do work, it can power a circuit. That's really, to me, was more significant. But honestly, I got so much mail about, well, you're not really doing anything useful. What if you charged a capacitor and you stole energy from the Earth? Then you'd be doing something. Now you're doing something real. So actually, we did do that. We did steal energy from the environment. Maybe we did something real. But now you're kind of wanting to go back to the earlier one. You realize in your question, well, what if I just use it directly?
Right.
That's an easier problem.
Okay, fascinating. Thank you.
Yeah.
Quick questions, James Lee and then Tom Vallone.
Yeah, Paul, it's a wonderful work and very solid. So pleased to see. As Daniel and also Garrett talk about it, it's actually your process actually be a very nice type B energy process we now discovered in my work, actually in biology exists in your body, in my body, in the whole world, actually. So yes, your individual component, as you said, you know, follow the second law very, very well. Okay, like your capacity charging, you know, all that. But your overall process, as Danny pointed out, you are doing extracting heat energy from, you know, charging can become useful energy, right? So you can do work. Actually, so you don't be afraid of, in that case, your energy B process, actually the second law does not apply. We'll talk about more about it. So don't be afraid, you know, saying, hey, you know, this second law does not apply, because you do see a phenomenon, you say getting something, you know, interesting, as you said, right? Unusual, right? Yeah, so no, that's my point.
Yeah, I agree. I think the second law doesn't apply because they're unbalanced forces. We're driving the system.
That's right.
Kind of like letting water go off a cliff. Of course, you can harvest energy from that. Yeah. And it's just out of equilibrium.
Yeah, so Daniel and I also talk about you have a symmetrical process there. When it's symmetric going on, as Danny pointed out, so the second law, to be careful. Sometimes you can apply, sometimes you don't apply. So that's my point. Thank you. Wonderful work. I like that.
Thank you.
Tom. You're muted.
Hey, Tom, I can't hear you.
Okay.
There you go.
Yeah, how you doing? I'm the author of a book on practical conversion, zero-point energy. I haven't corresponded with you yet, but I've been a great fan. And I wanted to call your attention to Johnson noise, 1927 Phys Rev, also Callan and Welton in 1951, and also Stumian. Those are references that might actually start you in the direction of including zero-point energy, 1/2 h nu. And it could be another factor that's adding to the input energy, especially if the temperature changes and starts to go down. That's the test for whether zero-point energy is a contribution. Koch or Koch, K-O-C-H, did experiments at liquid nitrogen temperatures, liquid helium temperatures actually, and still found oscillations and fluctuations that are available. So they're non-thermal fluctuations that could be contributing to the effect you're having.
Yeah, thanks for that. You know, I'm a big fan of Johnson noise and Nyquist's theory. That I pointed out the imaginary part and the real part here actually as kind of a nod to them, because that's really what he originally proved was the real part is the important part, kind of the power. But you can control the gain with the imaginary part. So that's an interesting factor here. But yeah, I never thought about the the zero-point energy here before, so that I'll take a look at that too. That's a good point.
I'll send you the books I've got and references, and hopefully help you along.
Thank you.
Sure, thank you.
Thank you. And I'm afraid we'll have to call it there so that we can take a 1-minute break before the next talk. So thank you again for a fascinating talk, and I look forward to talking more about this in the panel discussion with you this afternoon. So we'll reconvene in 1 minute.